Thank you. It was only last week that finally 21st Century Fox released the trailer for this summer's Fantastic Four movie. It's an excellent opportunity for us to go revisit the core material, its source. And toward the end of the hour, we'll take a look at that trailer. We'll see how well Hollywood has done with replicating the canon of the original Fantastic Four, the world's greatest comic magazine. And as a kid, my personal favorite. We'll look at the physics of the Fantastic Four. We'll look at the physics of their origin. While we go through today's lesson, the radioactive origins of Marvel Comics. I said today's lesson because I've given a number of these lessons before. For those of you that haven't participated, let me do a quick description of how this usually goes. And for those that have been in attendance before, it's a quick review. 2 summers ago, you probably watched Superman testing the limits of his newly discovered powers. And in the Man of Steel, we're reminded that Superman's power of flight is in fact an exhibit of jumping with super strength. In fact, that is how it was described in Action Comics #1, in Superman's debut. There it was explained that he's able to leap a 40-story building in a single bound, clear an eighth of a mile in a single jump. Information that with a high school physics textbook, you can go back and use to determine what the surface of his home planet Krypton must have been like. And in that first lesson, we in fact did that, and we determined that the G-force, gravitational pull on the surface of his origin planet, is about 47 times greater than it is for us here on the surface of the Earth. How many chemistry majors are there in the audience? Any chemistry graduate students? This is the origin of the original Flash, Jay Garrick. If you're a chemistry student, please do not smoke in your laboratory unless you want something really cool to happen. It's a chemical spill that results in him being empowered with the speed of the Flash, revisited in 1956 with Barry Allen as the Flash by inserting the added touch of a lightning strike in his laboratory, mixing with the chemical spill, which of course makes it more plausible how he got his powers, right? In the latest incarnation. Well, however it happened, in that lesson, we went on to explore the physics-defying feats that he exhibits, like running over the ocean, which we determined, in fact, was possible. Running up the side of a building, okay, if you're very careful. Vibrating your molecules at super speed so that you can actually go through solid objects. We'll have to come back to that. Tonight, though, we're talking about not what was happening over in the DC universe, but in the Marvel House of Ideas, where you may recall they featured a physicist, Dr. Robert Bruce Banner, bathed in gamma radiation, which, whenever he gets really hacked off, turns him into the Incredible Hulk. And where physics student Peter Parker is bit by a radioactive spider and endowed with the proportionate strength and speed of a spider. Okay, I always thought Marvel Comics was cool because of the physics. What was it that made creator Stan Lee, Steve Ditko, Jack Kirby exhibit this? They seemed so enamored with radiation and used it time and time again to explain the powers. You got to understand that at the time, late 50s, early 60s, nuclear physicists were the rock stars of that age, at least as measured by the number of appearances as they were featured in Look Life and Time magazine, and how many times they made the cover. Not everybody understood what they did, maybe not everyone remembered their name, but certainly everybody read about guys like this. James Chadwick, 1925 Nobel Prize for discovering the neutron. Charles Townes, did you read about him? Just a couple of weeks ago, he passed away at age 99. His work in the microwave application by the stimulated emission of radiation laid the groundwork for the ubiquitous laser. We have Townsend to thank for that. Enrico Fermi, his Nobel Prize was for demonstrating induced radiation, the idea that stuff that's not radioactive, when exposed to radiation, may become radioactive. Although what he's most remembered for is leading the project at the University of Chicago that first split the atom. Robert Oppenheimer, director of the Manhattan Project, felt for the rest of his life that he was saddled with the title Father of the Atomic Bomb. On the lower left-hand side, Edward Taylor, who was proud to be saddled with the title of Father of the Hydrogen Bomb. If you look at these characters and imagine in your mind an artist's conception of a composite that merged all these faces together and was intended to represent the combined knowledge of them all, I think this may be the image that's formed. That's Reed Richards, Mr. Fantastic, the leader of the Fantastic Four. And in fact, judging by the ubiquitous pipe he carried in the first couple of issues of that comic, I'm pretty certain that artist Jack Kirby was using Robert Oppenheimer as his model for Reed Richards. The gray temples, the lean face, and again, the pipe. This was the golden age. This was the good old days everybody talks about, when the promise of radiation made our future look very bright. This is an advertisement for, when I was a little kid, I had a wristwatch that had these luminous dials. They contained real radium. It's why you can't buy them anymore. But at the time, they were using them for lots of stuff. Electric push buttons were illuminated so you could find them in the dark. Buckles on bedroom slippers, house numbers, flashlights, compasses, gasoline gauges. Before I was born, but there was an ad by Union Carbide about the dramatic new developments in medicine, agriculture, industry, the promise of what atomic energy will bring to you. Here's an ad from Popular Science, 1955. Look what it says. Here's your chance to cash in. Over $3 million in government bonuses have been paid for uranium discoveries in the past 2 years. They were recommending everybody rush out and buy a Geiger counter. Or certainly if you're a hunter or a fisherman, you don't want to go anywhere without yours. They made these things sexy. They were shaped like guns. Something every homeowner was recommended to own. Back at this time, you could imagine nothing more wondrous than discovering in your own backyard a load of uranium ore. Of course, that stuff does have its downsides. That led to the cautionary tales that were sneaking into the B movies at the time. Gamma ray creatures on the loose, the Gamma people, Empire of the Ants, where Joan Collins here being threatened by radioactive ants, the amazing colossal man. This then was the age when Fantastic Four #1 hit the newsstands. It talked about a small team of 4 astronauts who went off in space in an experimental rocket ship with inadequate shielding. Going through the Van Allen radiation belts, they were exposed to cosmic rays, which mutated them into the Fantastic Four. This is a cast from the 2005 movie, The Fantastic Four. An okay movie, but this was immediately following the highly successful X-Men and Spider-Man franchises, so okay really didn't cut it, especially for the world's greatest comic magazine. If you aren't familiar with the Fantastic Four, let me explain what made them my favorite comic book. Reed Richards, the scientist, the leader of the Fantastic Four. The exposure to cosmic rays gave him the ability to stretch. And here you see him dodging, weaving, ducking, reaching across the room, avoiding obstacles. The thing that made him fantastic, however, was the science he was able to do. And in the Fantastic Four comics, they always returned to that. Here you see him in the upper left-hand corner empowering the transdimensional cannon now. Here on the right, I've already managed to create a primitive form of one-celled life. Lives for a few seconds. Do you think I feel like stopping now? There was some adventure that was taking him away from the laboratory. On the lower left-hand corner, he's testing out his Fantasticar. Here in the middle, he says, just a hunch. I've been checking the heavens for any unusual manifestations, and I've picked up some ultrasonic power rays beamed to the Earth from the fifth quadrant. How many quadrants should there be? His girlfriend, eventually wife, Sue Storm, was given the ability to turn invisible, which meant she could sneak in and take care of villains unobserved, but it was a power, the ability she had to warp space and channel the rays of light around her so that she couldn't be seen, eventually was something she managed to master into an invisible force field. There you see her stopping bullets. Her brother, Johnny Storm, became the Human Torch. And when flamed, he finds that he's lighter than air can fly. In the scene where he first appears in Fantastic Four #1, we see Johnny tinkering with his hobby, a car. When he sees a flare that gets his attention, and he gets so excited he flames on to follow it and leaves his car in slag behind. But Johnny Storm, the Human Torch, was something that various artists could display to fantastic and spectacular effect. Ben Grimm was endowed with not only rock-hard skin, but enormous power. Here you see him ripping buildings apart, and when he's not feeling so destructive, sometimes saving buildings from falling apart. That strength, however, came at a personal cost. It's this hideous appearance as a thing. This gave the comics its pathos. I look like a monster. I feel like one sometimes. And the few times that Reed Richards is able to, we believe, cure him and return him to human form, it never turns out to be anything more than a temporary situation. But for all that desperateness, he survives through a spectacular sense of humor that he develops. And it's actually the thing that gives the comic book its comic relief. Here you see him dispensing with show-offs at the beach. He's trying to get some sleep. He goes, I'll show you these weightlifters lifting some weights. Dealing with the bully with a flick of a finger. Waking up here, what am I doing between satin sheets? Like a half-ton Sleeping Beauty. Yeah, the thing was there for comic relief, but I don't think it was ever intended to be comic relief. But together, the Fantastic Four really were fantastic, and the adventures they had fit that descriptor. And when Jack Kirby was drawing, the instruments that Reed Richards built, sometimes so massive he needed the Thing's help in assembling them, were also truly fantastic. Around the room, I've got a couple of oscilloscopes, and if you're near one of them, you might turn around or lean in so that you can see it. I'm going to prop up my camera to give you a close-up of the one I've got here at the front of the room. What you'll see, if you look at any of the oscilloscopes in the room, it's an image that's continuously flickering. And it starts with I notice the camera inverts the image, so this is the mirror image. But it starts with a flat baseline that keeps retracing this spike that dips down. Let me get back to that in a moment. Those oscilloscopes, you'll notice, are attached to a large plastic square. And here's the mini-me version of it. That's actually a clear piece of acrylic that's been wrapped so that it's light tight and not visible. And attached to the top, peering into it, is a light-sensitive instrument, a photomultiplier tube, or PMT. There you see them up on the screen. The PMT is a device that, when exposed to light, it kicks off an electric pulse. And that's what the oscilloscope is tracing. So let me revert back to this image. What? There's a silver box by each one of these setups. That's a power supply. And if you are close to it, you can look at the readout at the top. Those things are set to apply more than 1,000 volts to the photomultiplier tube. I think that one's 1350, that one's probably 1480, this one's set up at 1220. It charges a bank of capacitors. What the oscilloscope is reading is the voltage across those capacitors, which normally, because it's attached to a power supply, is being held constant at the numbers that I told you the dials of this instrument were set. Which means the oscilloscope would normally just trace a flat, steady line, constant voltage. But whenever this sees light, the capacitor banks discharge. That's why you see the line suddenly take a nosedive. Since it's attached to a power supply, which is trying to hold it at constant voltage, it restores it pretty rapidly. And that's why you see that characteristic spike. Every time it spikes, it's being triggered by something, and that something is light that it sees. You know, when this thing is wrapped in black plastic, like this, there should be no light visible to it at all. The intention is this is light tight, which means the light that this instrument is being picked up is spontaneously being generated inside that clear plastic. The plastic is doped with some fluorescent chemicals. What creates the light is every time a charged particle passes through it. That's what instigates the generation of light, the flash that that thing picks up. If you can look at these oscilloscopes, look at the lower right-hand corner of its face, and you'll see, okay, this is reversed. So I said lower right-hand corner, it's over here on this one, and reversed. There's a constantly refreshed attempt to tell you how rapidly is the image being redrawn. If you look at it, it's flickering very quickly, and you're fooled by the naked eye. If you think you can look at that and count how many times it redraws each second, I don't think so. This thing tells me it's being refreshed at 129, 37, 56, 117, 80, 90, 97, 43, 60, 61 hertz. What's hertz mean? If that thing is tracing a spike, 100 hertz, that means how frequently is something triggering the PMT? The term hertz means per second. If something's being redrawn 60 or 70 or 80 or 90 or 120 times a second, that means 120 times a second, radiation is passing through this panel, any of these panels. You know what? You are an even bigger target than this panel. and easily several hundreds, if not thousands of times a second, the radiation that's triggering that is passing through you. About 100 years ago, Victor Hess took instrumentation aloft in a balloon to try to measure this background radiation. He assumed that most of it was coming from the radioactive elements that we know occur naturally all around us in trace amounts. The building materials, my God, the air we breathe. He was surprised to find that as he left the ground and got aloft, which should have made the radiation rates drop, they actually went up. Well, they dropped for about the first 100 and 150 meters. But after that, they started to grow. They doubled from 1,000 meters up to 4,000 meters and continued to increase beyond that. He got the Nobel Prize for his discovery of high radiation, which eventually got interpreted as radiation that's coming from the heavens. We now know, for example, that the Earth is surrounded by a belt that has trapped in it radiation. The Van Allen radiation belts have electrons and protons trapped by the Earth's own magnetic field. It's an envelope that when the US sent astronauts aloft, they avoided intentionally by taking off toward the north. They didn't want to go through. They knew that satellites that had gone through got overwhelmed by the radiation and sometimes were shut down. There were some fortuitous balloon experiments measuring this background radiation from the sky that coincide with the observation of solar flares that confirmed that some of this radiation, in fact, is coming from our own sun. But cosmic rays, in fact, come from all directions of the sky. But the sky is filled with stars. We assume that all stars, like our own sun, is giving off this kind of radiation. When Jack Kirby drew Fantastic Four #1, here's Benjamin J. Grimm at the controls. Geiger counters go off. Tick, 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 tick. Hear that? It's the cosmic rays. I warned you about them. They're penetrating the ship. Our shielding isn't strong enough. But I don't feel a thing. Naturally, they're only rays of light. You can't feel them, but they'll affect you just the same. Well, Ben Grimm is not quite right. Although Jack Kirby drew them as these little corpuscles that you could see coming through the ship, you can't see the cosmic. I told you we're being bathed in them right now, right? But look at this. This was a publication just in 2003. Astronauts had always claimed that when in orbit, they would sometimes, if they're in the dark, they close their eyes, they would get this impression that they could see little scintillations of light, little flashes inside, back of their eyes. And that was unconfirmed until experiments in 2003 verified that the cosmic rays passing through the vitreous fluid of the eye can do something like the cosmic rays that are going through this panel and generating light. Closing their eyes, yes, they could see some imagery that cosmic rays were passing through them. But they're not really rays of light. When they argued that the cosmic rays could pass right through you, and when I claimed cosmic rays were passing through these panels, if they're really cosmic rays and their origin is up in the sky, that means those things have gone through the building material that surrounds us, the steel, the concrete, the brick, the mortar. How's that possible? Well, you can appreciate that when you think about how small these things are. Ernest Rutherford and his student Heinz Geiger did the following experiment. They took a piece of radium, enclosed it in an apparatus with a small hole bored so that most of the radiation was shielded except for a little region where it could come spraying out unshielded. And they mounted a microscope that had a zinc sulfide screen at one end, that's the S, right there. And then they had a filament that they could put in its place, a thin aluminum foil, gold foil, copper foil, lead foil that they could drop in place. And they could view, by looking through the microscope at the zinc sulfide screen, the little scintillations that were evidence that radiation was in fact leaving the radium, coming through that hole, and landing on the eyepiece, on the reception end of that microscope. You'd look for it and you'd watch the little lights flicker, and you'd know radiation was coming through. You could swivel this thing, you'll see how it's mounted, so that you're out of the hole and of course see nothing, into the hole and see it, swerve it out and not see. And they could do it with the filament in place and with various films as a target in between. The radiation that they were looking at were alpha particles, alpha radiation. Alpha radiation are little subatomic fragments of a nucleus that spit out, and therefore smaller than the original atom itself. So this is a subatomic fragment, an alpha particle that's basically the same as a bare helium nucleus. It's a pair of protons, pair of neutrons, but suffice to say it's a little tiny clump of the nuclear material that's inside the original atom. That's different from a gamma ray that affected Bruce Banner, which is in fact little bursts of light. The alpha particle could serve as little subatomic bullets in Rutherford's experiment. I said they could have the source enveloped in a protective coating with a little hole bored to produce just a steady beam. You could swivel this microscope around to the opposite end and get in direct line with that beam, and you could count the particles coming through. If you put a target in the way, so a gold foil like this, then you could see if you had any effect on that beam. And you could swivel around and pick up any points where you may be ricocheting off those alpha particles. The astonishing thing was they discovered almost all of the radiation tore straight through that gold foil or lead foil or copper foil. And just the barest fraction of that beam ever bounced back. What does that mean? That means even in solid lead or solid gold, there's actually a lot more empty space than there is solid material comprised of the atoms themselves. Particles like the alpha particles can go through stuff, even lead. That's why the cosmic rays are going right through everything and through you. They pass through us harmlessly, I promise, thousands of times a second. But I wouldn't worry about it because human civilization has endured its whole existence with that sort of background radiation. We're hardy enough to survive, I guess, and you shouldn't be freaked out about that because, my goodness, about 1,000 times per second, there are spontaneous radioactive decays inside your body that are generating radiation. About 2 trillionths of the carbon dioxide that you breathe in carries carbon-14. That's a radioactive brand of carbon that beta decays. Table salt, about 2,000ths of it contains the sodium is displaced by potassium-40. That's an alpha emitter. The very food you eat, the very air you breathe, radon, decays by an alpha decay to polonium, which then follows a series of decays of alpha and beta decayers. And you know, here in Nebraska, that's to be found in the air that leaches up through the grounds and into our basement. Thousands of times per second, cosmic radiation from the outside is passing through you. 1,000 times a second, radiation internal is working its way out from within. But they do usually pass straight through you harmlessly. I describe the passage of these things through us as tickling the atoms that they pass by. If an overwhelming fraction of them pass right through unperturbed, if they're charged, and these cosmic ray subatomic particles are, they are mostly protons, some of them are alpha particles, but being charged, they can zip past an atom, but the electrons, which are charged, will notice and may be excited or even ionized. We're mostly 2/3 water, so the passage of all those charged particles through us all the time, they mainly set the normal level of pH in our cells and do nothing more than that, or not much more than that. But what about that small fraction of them that don't just pass through, that actually clobber the nucleus of an atom? In the rare instance that a cosmic ray actually damages a cell, it's actually no big deal. Who'd notice? Every time you bump your knee, skin your elbow, bite your cheek, you kill thousands, if not tens or hundreds of thousands of cells. You survive. Your body just flushes them away. In fact, we're constantly shedding dead cells to the tune of about 1 million a second. So if once in a great while a cosmic ray destroys one of your cells, you're not going to notice. How often, however, might that damage actually be a mutation of the DNA? And how often would such a mutation be harmful? How often would it be beneficial? How often would it do something cool? Well, it's less than about 1.5% of human mutations per generation are harmful. And in a much smaller fraction are beneficial. And the number of them that get copied and selected to survive the generations is minusculely small. Those you need enormous amounts of time to ever see in effect. 98% of all mutations are utterly neutral. They don't seem to do anything good or bad at all. Okay, 1,000 times a second, cosmic rays are passing through you. 15,000 times, oh, I think I missed a slide. Let me back up. You know, your body is this complicated system of organs organized into tissues and cells. You've got over 75 trillion of them, and if you wanted to count the individual atoms, that would be 7 times 10 to the 27th atoms. If 1,000 cosmic rays are coming through you every second, if you went through the Van Allen radiation belt, which I guess the Fantastic Four must have done, it can be as high as 15 million times per second. You know, if you've got 75 trillion cells in your body and 15,000 times a second cosmic rays are passing through you, how long would it take for you, on average, to have every cell in your body irradiated? It'd be about 5 million seconds. So if you bathed in the cosmic rays for a little more than 8 weeks or so, you might get a full body dose, exposure of every cell. Oops. But when the Fantastic Four went through the belts, there was a simultaneous cosmic ray storm, a solar flare. Solar flares can, in fact, increase the dosage of cosmic rays on the Earth 10 to 100,000 times more. If the Fantastic Four went through the Van Allen radiation belts and a solar flare triggered a cosmic storm, in a matter of about 7 or 8 minutes, yes, they could get a full body dose. Now the handout that I had you look at. You don't have to go through it now. You can do it at your leisure. My intention was to remind you of how probability worked with some simple examples to help frame what I want to describe next. Being immersed in gamma rays, like Dr. Bruce Banner, or cosmic rays, like the Fantastic Four. Exposure enough to guarantee that every cell in your body had the chance to be, an equal chance to be radiated. That doesn't mean necessarily that every cell in your body did. Here's a plot of a simulation of 1,000 trials of tossing 1,000 coins. If you tossed 1,000 coins, how many heads would you expect in any toss of 1,000 coins? Each coin has a probability of a half of coming up ahead, right? And if you got 1,000 tries, how many heads do you think you'd expect? 500, right? But notice that doesn't guarantee you'll get 500. In these 1,000 trials of 1,000 coin tosses, sometimes they only got a 450 some. Sometimes they got 550 some. It sort of clumps around and certainly averages about 500, but there's no guarantee that you see the 500 every time. Here's the relative probability of getting n sixes in the toss of 12 dice. On this worksheet, I lead you through the steps so that you can calculate this yourself. If you tossed 6 dices, how many sixes would, let's see, 12 dice. Toss 12 dice, how many sixes would you expect to be reasonable to see? 2, right? Because the 6 has a 1/6 chance per roll of showing up. And if I look, the 2 has the strongest probability, but it doesn't guarantee that you'll get 2 of them every time. Look at that spread. And in fact, it's possible to get all 12 of them, but on the scale of this plot, I don't see it. I'm going to jigger things a little bit. First, I'll recognize that there's over 2 trillion different outcomes possible, or 2 billion outcomes possible when you toss 12 dice. I'm going to convert that to a logarithmic scale. Notice what the logarithm does. It foreshortens the big steps at the high end of the plot, and what it'll, like an accordion, and it'll magnify things at the low end of the plot that are imperceptibly small at the moment. So that you'll see there really is a chance, one way, to get 12 sixes, right? But that's only 1 out of that over 2 billion. So the probability of getting all 6s is pretty dang small. And here it looks like the probability of getting 1 or 2 are almost the same, but that's a trick of the logarithmic plot. Remember, there actually was a step between those, and the 2 is a little bit stronger. You see that in the raw numbers here. No 6s, 1 6. This is the number of way of getting 2 6s. When you're dealing with things like cosmic rays, where the probability of it interacting with the cell as it passes through your body is incredibly tiny, then you need to have an observation of many, many, many chances of cosmic rays trying again and again and again to nail that cell. So you may have to give it billions of shots to see any outcome. When you do that, the way you calculate the probabilities are similar to what's described for flips of coins and rolls of die on those worksheets, but Poisson statistics are used. And if you use the Poisson statistics, if I've irradiated a body sufficiently that on average I expect every cell to have a pretty good chance of being illuminated once by a cosmic ray, then watch this. That's only the average, right? On average, I've given it enough time to expose them all. But the percentage of cells that'll probably be hit once is a little better than a third. There's probably an equal number of cells that were missed entirely. No hits at all. Clipped a neighbor twice next to it. The percentage that are hit twice, thrice, 4 times, there's a spectrum. Out of those 7 trillion cells in your body, if you've got a full body dose of radiation, about a third of them probably got hit once, and a third of them have been missed. Can you imagine being the Human Torch, flaming on for the first time, and only 38% of your cells are flame retardant? Ouch. Okay, that was only the odds of having each cell have a cosmic ray pass through it. Remember what the odds of it actually forming a mutation? Or the odds of that mutation being anything cool? then think about the odds of every single cell in your body being affected in the same way. Stretchiness, rock-heartedness, flame. Excuse me. So even if one of the Fantastic Four were endowed with powers as a consequence, it would be astronomically small odds to expect any of the other members of the team to also survive like that. When might exposure to cosmic rays actually have an impact on the entire body of that organism? You and I, bathed in gamma rays, cosmic rays, whatever, okay, may damage some of our cells. When might it do something that would infect the entire body, not just some of the cells? At an embryonic state, and that's the slide I had slipped to already. You know, when the human organism is just a cell or two, then being bathed in radiation can infect the entire organism forever. Or perhaps even more effectively, what about an exposure to the reproductive systems of the parents? That, of course, and in fact, the tagline for the original X-Men comics was "Children of the Atom." Where did they get their powers? Well, Charles Xavier, Professor X, his father, nuclear physicist. In fact, very telling, his mother was a cancer victim, he himself was. Scott Summers, Cyclops. His dad was a NASA test pilot. Remember, the cosmic radiation is much higher aloft than it is here on the ground. Hank McCoy, his dad worked at Lawrence Livermore National Laboratory, a physicist, say no more. In fact, we know that the simple mistakes of copying in the split of a cell can have dramatic effects on the resulting birth. Multi-limbed creatures, multicolored creatures, trichinosis here. Combine those together, you can make lots of X-Men, right? And realizing that, I think, like me, each and every one of you sometimes dream of tomorrow may be the day where that X gene kicks in and you wake up with fabulous powers. About late 2003, early 2004, recognizing what Hollywood remakes can do to even treasured icons, Marvel released a new imprint. This was the Ultimate Comics line, in which they tried to do their own Hollywood makeover and revisit all of their stories, updating the origins. And this was the Ultimate Fantastic Four. So this is a new take on the Fantastic Four, a new universe, a new Marvel universe. And if you'll notice, they look younger than the original Fantastic Four. In the original Fantastic Four, a grown-up, mature Reed Richards discovers an adjacent dimension that he can peer into. He calls it the negative zone. He builds an instrument that opens a portal that allows him to go inside and explore. But in the Ultimate Comics, Reed Richards is a boy super genius who does that as a science fair project. So here you see young Reed Richards with his friend Ben Grimm, and he's sort of explaining to him his device. And did you catch it? That scene was in the trailer. That's young Reed Richards and his childhood chum, Ben Grimm. So that's in his garage doing his teleportation experiment, trying to pierce the next dimension. This is Miles Teller as a young Reed Richards, and pretty much looks the part, not bad. This is Kate Mara as Sue Storm. Michael B. Jordan as Johnny Storm doesn't have quite the blue-eyed blonde appearance of the original comic book. But notice he's working on a car, and you saw that in the trailer. And I can only hope there's a scene where he has to flame on to get out of there and ruin the car in the process. And although in the comic books Ben Grimm was a football hero, here I see him on baseball field. Okay. And apparently we're looking at some view of some part of him as the Thing. So we've got to see some more images before we know how much this thing looks like the one we know from the comic books. Even though this is some sort of teleportation device, I have to give credit to Josh Trank, the director. It has the look, it has the feel of the launch pad for a rocket ship. And Josh promises that he wants to respect the origin of the Fantastic Four. In other words, irradiated by cosmic rays and endowed with their power. Somehow those cosmic rays are as they pass through the dimensional portal instead of going up into space. More than that, it's hard to tell from the trailer. So all I can say for now is to be continued. And if you've got questions, I'm happy to take them. Yeah, please.
So the original Spider-Man, when he was bitten by the spider, his atomic composition changed. There was no mention of genetics, and the atoms changed structure. Right?
So you'll notice in the movie, it's all about genetics. But in the original, no. But also in the original, he isn't changed instantly. This takes days to work through his system. But Stan Lee wasn't much of a physicist. And his level of sophistication of understanding radiation and what it might do to bodies, not so clear. But I agree.
And I think as these reboots and remakes keep getting more updated, they become more and more genetic.
That's right. That's right. In fact, the whole Ultimate line abandons the radiation as the source of most of the comic book heroes in the Marvel universe in favor of some sort of genetic experimentation that creates them. Yes?
You think about the probability, is it affected by, when they have a team of people, they have to, there's the probability that this would occur, and it would occur at that level, but then with that many people, is that a level of statistics, or are we assuming that if it happened at all, it would happen equally to all four?
It would be, you roll the dice. Roll 12 dice, and they all come up sixes. Okay. Let's say that happens, and that's one person being transmuted successfully into a superhero. If each of these had to roll those 12 dice and hope for the same outcome, that's very unlikely. Now, in this Ultimate universe, this teleportation actually is described as taking you through an antimatter dimension. And to do it, Reed Richards has to change the CP phase of every atom in your body to do it. And somehow, the argument is, when they return, not everyone has been changed by the correct amount of phase to come back as they left, and the differences between each of the four are because they're all in a different phase. The level of sophistication grows exponentially with each reboot of the series.
Have we ever reached a really bad solar flare, and what's the likelihood that we're going to get a really, really big one?
Well, you might remember back in, was it November? There was a huge flare, and warning went worldwide to brace yourself because they were expecting that they might blow out the entire electric grid. Didn't happen, but they know that it has happened in the past. That sort of thing is something that will happen from time to time. Something even worse, well, hopefully that's much rarer.
But we've never had a grid before.
And we haven't had a grid before, so that's true. But smaller parts of local grids have been blown in the past by cosmic storms. Okay, thanks for coming. I hope you enjoyed it.